Great. Thank you very much to the organizers and to the participants for being here. Um, and so, yes, I'll be talking about negative capacities from gauged matrix and tensor oscillators. This is work done with with Denjo O'Connor over the last year or so, where we talked about basically gauging finite group symmetries, where you have your matter degrees of freedom being matrix degrees of freedom, and then setting up path integrals, calculating explicit partition functions, and then extracting some physics, and then finding that these naturally give rise to negative specific heat capacities. We first found this phenomenon in this finite group symmetry setup, but they also exist in continuity setups. So the examples I'll talk about will include both of them. So just to get started, matrix quantum mechanics models have very interesting thermodynamics, which have been interpreted in the ADS correspondence. And the mathematics behind the counting of polynomial functions of matrices, variables, or tensor variables. And we're looking at functions, polynomial functions invariant in the appropriate symmetry group. And so within this world, it is there are very natural occurrences of the heat capacities. And some of these examples may well be of interest with small black holes in ADS-CFT. So to show you some of the simplest examples of the counting and build up from the counting of states in the simple examples to the more complicated examples and see how the partition functions change. I'll just remind you of the basic examples of n equals 4 super Young-Mills, where you have 6 Hermitian matrices. You take a pair of them, form a complex combination, get a complex matrix, and look at polynomial functions of that. Essentially trace tricks and powers of traces of powers and multiple sources, so multi-trace operators. These are the kinds of things that are very interesting in T. And CFT gives us an inner product on this space of states. And the free field inner product is very important in the half PPS sector because it's not renormalized and it contains a lot of physics of the strong coupling limit. Now, this free field inner product can be also captured purely in quantum mechanics. So you can just have a quantum mechanical model with quadratic potential, and the same inner product arises from this very simple setup. Because it's a complex matrix, you have 2 oscillators, A dagger and B dagger. And the kind of half BPS sector or the holomorphic matrices holomorphic functions corresponds to taking just essentially states related to one of these oscillators. So counting of such things, you just simply count multi-traces of one matrix. So if you have total energy 3, you can have a single a trace, or 2 traces, or 3 traces, depending on how you distribute your 3 oscillators in among these traces. So 3 equals 3 here, 3 equals 2 plus 1, and 1 plus 1 plus 1. So these are partitions of the number of the energy that you have. So counting is simply counting of partitions. Now, very interesting thing about that, well, already you see that there's an important qualification, is that if it's a 1-by-1 matrix, then it's A dagger 1, 1 to the 3rd power, and all 3 are actually the same. So the counting, there's a generic counting that holds when the matrix size is large enough, as the matrix is bigger than 3, this is the counting. But when the matrix size is smaller than the energy you're thinking about, the important qualitative changes. So basically, here we are. The counting is given by the partitions of K. K is the energy, and this is independent of N as long as N is bigger than K. But the counting is changes when the number of size of the matrix is less than k. So there's this full range, which goes like counting of partitions, the asymptotics of that like e to the root k, and then this finite. So this is quite generic in all the countings that we're going to talk about. There'll be a stable, and there are some well-defined corrections when you have finite n effects. And these different kinds of, there'll be different kinds of large K asymptotics, which will lead to different kinds of thermodynamic behavior, finite temperature Hagedorn transitions, or zero temperature, and in some cases negative specific heats, which will be, a lot of that can be sort of guessed by knowing the right form of the large K asymptotic in the stable regime. So the next example involves two matrices. If you have, for example, the new thing now is that the order within a trace is important, and that a great increase in multiplicity. So rather than e to the root of partitions, we get something much bigger. We get growth of the counting of states, like e to the k now, not e to the root k, but e to the k. So exponent. So now if you look at the thermal function, e to the minus beta k, k is the energy, this is the degeneracy. Now, depending on whether beta is smaller, this will converge or diverge. And as a result, there is this Hagedorn transition. So for T, small temperature, large beta, this dominates, this converges, all good. But then you have a Hagedorn transition, at which point this term starts dominating the negative. So this is the confinement transition that has been discussed. So this, just the free counting shows this very interesting feature of transition. Now, just a little bit this finite group stuff. Well, one of the kind of applications of matrix models beyond quantum mechanics and so on, pure statistics. So you can use matrix models to write down some probability distribution over the space of matrices, and these have been used to analyze statistics of real-world matrix data. Work of Wigner and Dyson, energy levels of nuclei, energy, space level repulsion, and so on, come from very simple things like this. Have been applied in other areas of physics as well. So, things you might ask is, what if I kind of start this sort of invariant under ON or UN, depending on whether you think of matrices or Hermitian matrices or just real matrices. In any case, this simple kind of under continuous symmetries. But what if you replace these continuous symmetries by discrete symmetry? What happens to these actions? And in particular, let's say we want to look at Gaussian actions, which means at most quadratic terms, linear terms, and quadratic terms. And now, instead of having a symmetry, let's say M goes to UM dagger or UM U transpose for all ON or UN matrices, you just restrict the invariance to be the U is a gauge symmetry now that you're going to impose. U is simply in Sn. So what happens then? Counting of the invariance, instead of counting traces, you're counting something very simple still. At linear order, so the permutations will act both the left index and the right index at the same time. So if you well, this is the trace, it's invariant under UN, ON, OSN. You have something like a sum of ij, mij, because the permutations act on these indices, and you're summing these indices. Therefore, this is also invariant. So you get two invariants rather than one at linear order. And for quadratic terms, you get more. There are 11 invariants, and there's a very nice counting of these invariants in terms of graph. So you have, for example, some of the usual Mij, Mji, trace-like things. But you can also have something like this, some of Ij, MKL, just the sum of all the indices. And the graph theory interpretation has to do with associating an index to code and a matrix to a directed edge. That's Mij, MKL. So stop accidentally? It's okay, maybe you can hear me anyway, right? So yeah. Anyway, counting of these invariant functions is associated to a counting of graphs. So these kind of Gaussian models have been studied and applied to real-world data in some sequence of papers, and that sort of brought us into permutation invariant models. Now, an important point here is that this counting, as I said, is graphs, and it grows very rapidly. 2 at linear order, 11 at quadratic, 52 to 96, and so on. It's growing faster than the counting of partitions. Then we started bringing this kind of counting and sort of exploring of this state counting in quantum mechanics. Now you have a matrix X, n by n matrix. You try to count the thermal partition function, and you want to really make sense of gauging the SN symmetry, and you can write down partition functions and part integrals that will do this. The trick is that the thermal partition function of this thermal circle, thank you. You can discretize it, and then you can make sense of what gauging that symmetry means, because now when you discretize things, you have a transport operator and there's a group element that's in a finite group easy to make sense of, whereas the connection is harder to make sense of. So this kind of work was done by Denjo, O'Connor, and collaborators for the case of continuous symmetries even before, adapted to discrete symmetries, and then you can start from the path integral formula and get some nice answers for what the counting is. So for counting, the thermal partition function reproduces a nice Mollien-Weil formula for the counting of invariants, which is given in terms of a determinant. That connects with the physical idea of gauging this symmetry. So that's a motivation for studying what these partition functions look like. So in the next, we'll talk about these partition functions in the SN case, talk about the thermodynamics in the canonical and the microcanonical ensemble, and how negative specific heat capacity arises, and the other things I'll develop depending on time. So, great. So we have the counting of states. We have matrix, the single matrix. First, now forget about the gauging. So if you just count this simple harmonic oscillator, just the n square oscillators. So you're just counting. This is the energy will just be the number of oscillators. You can build the junction e to the minus beta e times the degeneracies. While at leading order, there's ground state, there's n square oscillators, and at quadratic order, you symmetrize this n square thing, so you get this number, and that's what you're going to do to get the. And that has a counting function, or a function of e to the minus beta written as x, has this very simple form, and that's simply the trace of e to the minus beta of the Hamiltonian space, which is spanned by these oscillators. When you do the SN gauge theory, what you're counting now is simply the SN invariant thing. So there's a projector which acts in some appropriate way on this Hilbert space, and you have to insert that projector and do this counting. And so the Hilbert space at k level is some k oscillator Hilbert space, e to the minus beta k, and you have to in projector. So that's just what this is saying. Now, what exactly is that Hilbert space of k oscillators? Well, it's actually the symmetrized tensor product of taking the A dagger ij, that's the Vn transform n tensor, and the natural representation of Sn with itself. And then you have k copies of that because they're k oscillators. But then there's a symmetrizer because they're bosonic. So there's a projector for that symmetrization in the Hilbert space itself. So at the end of the day, you can write this partition function in terms of, at fixed energy, in terms of something very simple, tracing is just the ordinary tensor product space with a projector for a symmetric Sk and a projector for Sn. This is for the bosonic symmetry. This is for the gauge symmetry that you're introducing. And that can be calculated. So it can be calculated in surveys partitions of n and k, and for the gauge symmetry, k for the bosonic nature, symmetry factors associated with the partitions. There's some of n, partitions of k, symmetry factors, and there's a nice sort of coupling between the two partitions. You have a product from I equals 1 to k, and you have a sum over, so these i's represent cycle lengths for this sk partition, and then there's a condition that L, which represents cycle length for the Sn, that length has to divide the cycle length for the Sk, so you're summing over divisors, and then so there's kind of a nice formula that's quite concrete. And that was kind of worked out in the context of this sort of data science motivations. And this formula has this nice stability property that when the energy is less than K, you have some universal form, and then there are more complicated things going on when the size of the matrix becomes small. Now, so to do the thermodynamics as a function of temperature, you want to get a nice formula as a function of x, which is the temperature, or e to the minus beta. To do this whole sum over all energies, and then that can be done, so that sum over partitions of Q now disappears because we want to sum over energy, so multiply this by x to the k sum over all k. So we have to do this, and that again takes a very nice form. It involves integers, LCMs, least common multiples of them, the GCD, and so on. So one can get a very nice sort of form which can be obtained either from this projector stuff or from the Moulin-Weil formula, determinant formula that comes from the path integral, and then you work out in detail what it means for Sn. You get this. So we get this formula, for finite temperature, and coefficients of this can be the numbers at each energy. So great. So now we can see the dynamics of this. So we know the partition function, take the derivative with the inverse temperature, get the expectation value of the energy. It's convenient to divide by n squared. That'll be the energy per particle in this n square system, n square matrix oscillators. And these quantities have nice large n sort of behaviors. And you just plot the energy as a function of temperature, and you see as a sharp transition at some temperature, finite, for fixed n. And then as n increases, you still have a sharp transition, but that transition go and lower temperature. You can work out the specific heat capacity. There's a peak where that jump was, and again that peak recedes to lower and lower temperature as n increases. And that is sort of expected, because what will happen in the infinite n limit is that this transition, this peak will become higher and higher, and this will go to 0. And this is sort of something we expect, because as n goes to infinity, we are in the stable limit, where the counting is basically the counting of graphs that doesn't know about these finite n effects, just like the counters. So there was counting of traces led to e to the root k, counting of these graphs leads to something like k factorial now, so much bigger than e to the root k, so e to the k log k. Now this, for any finite temperature, any finite beta, for large k, this always dominates, so this will never converge. If you first take the large n limit and then do this, you converge at any temperature, no matter how small. So at large n, so now we're doing finite n and taking n to infinity, expect this sort of feature to reach 0. I guess just by looking at the stable sequence. So kind of 0, what was called 0 temperature hagedorn, was observed in the context of tensor models. It was recognized that these very high growth, very big degeneracies are associated with something like a 0 temperature hagedorn transition. So here we have explicit formulas for the finite n story, so we can approach that very explicitly. So now we can do this in the microeconomic. Here you look at the degeneracy as a function of n and k. There's an entropy. You can get the inverse temperature by taking a derivative of the entropy with respect to t. And entropy is now in the stable limit log k. And when you take a derivative, there's k1 derivative, which gives a log k. Take a derivative of log k, you get a 1. So 1 plus log k. Important thing, T inverse is increasing as k is increasing. So temperature is decreasing, is increasing. So it just simply follows from this k factorial behavior. They're going to get something where I've plotted energy versus temperature here. And this is the stable region where finite energy kicked in. And you're seeing this negative specific heat as temperature is increasing, energy is decreasing. And then at some point, these end effects control this very rapid growth of states. And then you just get a turnaround from negative specific heat to specific heat, and this starts behaving like n-square harmonic oscillators. And at high temperature, the gauging doesn't matter. And you get very similar to harmonic oscillators. This kind of counting, there'll be a very large region, as much bigger. This transition happens at order n log n, energy order log n. So as n goes to infinity, this will become very large, and there'll be a big region of negative specific heat capacity. So, and there's also a form, yes, that's the n log n that we've got numerically by fitting where that turnaround happens. Now, so I mean, it is a feature of the finite n or large n. In the large n limit, let me get. So you might ask, but we've heard we shouldn't have negative specific heat in simple systems. Well, in the canonical ensemble, you won't have this negative specific heat. So because there's a very simple calculation here. So large N is like infinite volume. But then from the sort of thermodynamics, maybe you should look at energy per particle, which is what we're looking at. And then, so there will be a sense in which canonical and microcanonical agree in the large N. Maybe I'll tell you about that in a second. So in canonical ensemble, the specific heat derivative, you can work at the dispersion of the energy, and it's always positive. So basically, if you plot that energy versus temperature in canonical ensemble, in the place where, in the region where you're getting negative things, that's around where you're getting this transition. But this slope is positive, so that's the canonical one, and that's a microcanonical one. And once you go beyond the transition, they will agree. And then, if you think carefully about scaling the and taking the large N limit, then, as I said, this will go to 0. I said this was n log n over 2, but when you take the energy per particle, it'll be log n over n. So this will decrease down to 0. Somehow all this funniness will happen at 0. But, depending on what kind of physics you're looking for, small black holes or whatever, that this is an important branch. Very, very similar curves happen for small areas. So we actually have an analytical, well, yeah, we do have an analytical argument. Exist because this comes from the k log k, or k factorial growth, and this high temperature behavior can be from the path integral itself. Oh, the location. So actually, we don't have an analytical argument for this n log n, but we do have an analytical argument for where this transition happens. I'll tell you about it shortly. And I think this is a bit correlated, these two things. Yeah. So indeed, so this transcanonical ensemble, that we can get an analytical argument for. So this partition function, was a sum over this SN functions was a sum over partitions of something that depends on partition, and the form of that, there are different powers of 1 over 1 minus x. So I gave you this formula before. So there are powers of 1 minus x in various places here. And if you pull out the power of 1 over 1 minus x, that power is something which we call the degree that depends on n and depends on the partition. And then there's something which is regular as x goes to 2. So the power of 1 minus x, again, it's a sum over the parts of the partition I length, so cycle lengths, if you like, simplicity square, and then the GCD divisor of the pairs of cycle lengths and so on. There's a formula here which tells you how much what power they contribute. From this formula, you can prove most singular terms come from simply the partition corresponding to the identity, and the second most singular comes from when the cycles in the permutation are length 1, there's a single cycle of length 2. Somehow, being term in this high temperature limit come from small cycles. And so this is high temperature because x goes to 1 that goes to 0, 1 over t. So 1 over t goes to 0, t goes to infinity. So high temperature is essentially a high temperature expansion. You can look at the first two terms and you can say, where does the second term start becoming comparable to that? So when does it become a, some small number a, order 1 number, let's say 100th of that? So where does that? And you can solve for what x will do that, and you get n over 2n plus some 1 over n corrections. So that gives you an estimate for where the high temperature expansion will break down, and the high temperature, the lead temperature is just doing that. Where does it start breaking down? It's an estimate for where this is happening. So that's at log n over 2n, and indeed as n goes to infinity, that's going to 0, which is 0 temperature. So yeah, so we do have an analytic formula for that. It would be nice to get analytic formula for the energy itself. Maybe there's something to do to, hopefully that should be doable. We can also look at the specific heat capacity as a function. What is the peak of the specific heat capacity at the transition point? It seems to behave like n log n. This is numerical. So it would be nice to understand these features a bit more, kind of build a model for what's happening at that transition. So to summarize, when we look at UN symmetry, we had e to the root k growth when to infinity. We had e to the k log 2 for the 2 matrix case, finite temperature. Here we got 1 matrix but discrete symmetry, e to the k log k, with a 0 temperature Hagedorn transition. So then look at different types of growth and say, okay, when can I get this negative specific heat capacity? Essentially, second derivative of the entropy is what is important, and you can get super exponential growths that do that, like this k log k, or small variations of it. But if you look at it, you also find that there's a sub-exponential growth that can also do it. E to the k log d, or k times this is exponential. But then if you correct this k by logarithmic terms, then it turns out that if a is negative, so that will be slightly sub-exponential, that will also produce negative specific heat just by taking the derivatives. So something like near exponential, but sub-exponential. So that can also do that. So there are similar systems where these other behaviors happen. If you take an index tensor and you impose, let's say you have a complex transforming in the tensor product of fundamental representations and its conjugate in the conjugate representation, and that produces a counting of invariant quantum states, where again you have oscillators with these holomorphic or fundamental indices, anti-fundamental indices. Invariant things look like that, attracted, the first with the first, second with the second, third with the third. But you can also have polynomials in A dagger, polynomials in B dagger, and you have to construct like the first index in all possible ways. There's some permutation that will do that. First index contraction, second index contraction, coming from a triple of permutations. And then there's some kind of bosonic symmetry. Well, there's a bosonic symmetry of these things, which leads to some equivalences. And that can, and there's a nice formula for the counting as a function of the size. These indices, I goes from 1 to n. If you're looking at states with energy little n, there's a counting of this, counting, where you sum over triples of Young diagrams with little n boxes, and the lengths, the heights of these Young diagrams are no bigger, capital N, and this is the number of invariants, number of representations in R tensor S tensor T, which is the Kronecker coefficient. So a formula, group theory formula for this. There's a large n asymptotic as well, which is n factorial, and this asymptotic estimate is what, again, n factorial, or k factorial in what I said before, my notation before. Again, k log k type behavior. So again, this has this negative specific heat, which is controlled by the finite n effects, and which the large can be worked out from the path integral. So you use high temperature behavior, and then for low values of capital N, you can plot the data, you can see how there's this negative slope, and it just starts down. Things become harder to compute as the energy becomes high and capital N becomes high, because this form too easy. I mean, you can code it, but not too easy to get numbers, let's say for n equals 30, for any energy equals 40. It's not easy to do this. In the SN case, we had this explicit product canonical. It was easier to work with that. But anyway, there's enough to get some evidence of this turnaround. And then the next, so can you do this in all models? So you can, so you complex matrix model, just UN transformations, and let's introduce another U1. So let's say Z is going to be charge 1, Z dagger is charge -1. We're going to now start looking at gauge invariant functions of Z dagger. So traces involving Z and Z dagger. So it's essentially a two matrix. But we know two matrix problem leads to e to the. But if you put the condition that the number of Z's is equal to the number of Z dagger, so neutral under this U1, there's a reduced counting. And everything looks like as a function of energy n, little n, the n, but it's corrected by 1 over root n. So it's precisely the kind of correction that leads to negative specific heat. So here we have plotted for n equals 13, this of a few sort of points that will, there are just only 3 or 4 points like this, but then this chaotic behavior takes over, and then you get this nudge, and then at high enough energy, it starts turning around. So if we start doing this, with higher n, there will be just a few points, and then this branch will start becoming longer, because this operates whenever capital N is much bigger than the energy. Capital N becomes much larger, you have a bigger range where the stable regime works, and you're going to get negative things, and then at high temperature you can work out from the path integral it should become positive. So you see the same feature in this case. And this plot was obtained again by some group theoretic formulas. So let me just see how much time I have. 10 minutes. Okay, great. So I don't to rush too much. So summarize then. There are 3 different examples where we saw very similar features. the one matrix discrete symmetry. There was this K or K factorial growth when capital N is much larger than K. And then in the 3 index, the UN tensor 3, there was again either K log K, so very similar. 0 temperature Hagedorn, negative specific heat capacity, and then there was here 2 matrix case with UN, where we had a growth of e to the K log 2, but corrected by root K. And now there was a finite temperature and negative specific heat capacity very near that Hagedorn. So you have to be very near, maybe scale you have to take a double scaling limit where the temperature approaches the Hagedorn in a way that scales with n, or maybe 1 over n. And in that very small region, you will see negative specific heat capacity. So basically this large n and appropriate scaling limits is what is needed to see physically this happening. So this heat capacity is arising purely from counting in harmonic oscillator systems, interactions, and people have been discussing how do we get to matrix in the 2 matrix model, for example, negative specific heat capacity, and it was conjectured that maybe if you start with actions, this e to the k will get modified, and maybe the interactions will produce negative specific heat capacity, which is of course the right thing to look for small black holes, which is a very interesting phenomenon in the dual ADS. But here you see you can from putting a constraint on the 2 matrix counting. Look at equal numbers of X and Y matrices or Z and Z dagger matrices, and you get a feature. And as I said, we have this we were able to derive in ensemble. Would be nice to derive the energy at that transition in the microcanonical ensemble. Should not be too unrelated to this, but one needs to think it through. Analogous analytic calculations for the transition in the tensor model or matrix model are not known because we don't have set partition functions. We only have these group theoretic ones. But these group theoretic things show enough, with these curves that features are happening. So as well, for this audience, maybe this is the most familiar thing, that small black holes in ADS, they have a mass formula as a function of the radius of the black and the radius of ADS, and they have a formula for the temperature, Hawking temperature. Using that, you can see similar behaviors at small radii. There's negative specific heat capacity, and when the radius of the black hole becomes large compared to the scale, then you start getting positive specific heat capacity, and they build applicational thermodynamics. So based on that, so would be nice to take these quantum mechanical models a bit closer to more complex situation where you have this small black hole interacting with gravitons and things that are happening inside ADS. So you want to couple this to degrees of freedom to emulate whatever this small black hole might be coupling to. Obviously, you want to study time dependence, as Niels talk, very interesting, and he also mentioned weak coupling n equals 4 super Young. So 2 matrix setup was very much right there. The 0 coupling limit of n equals 4 super Young-Mills is 1. So there is a lot to explore. Yeah, hopefully there's a feature there that exists of systems, and it'll be good to map this out a little bit more systematically. And I'll stop here.